Our galaxy holds secrets that defy everything we think we know. We often picture the Milky Way as a serene swirl of starlight, but that is only the surface. Look deeper, and you find a cosmic attic packed with relics and oddities, each with a story that challenges our understanding of the universe. This is a journey to the very edge of that understanding, where we will uncover 25 of the strangest objects hidden within our home galaxy. By the end, you will see the familiar night sky not as a quiet backdrop, but as a stage for some of the most dramatic and bizarre events in the cosmos. We will encounter stellar zombies that refuse to die, phantom signals from the void, and gravitational anomalies that pull on the fabric of space itself. What do you believe is the most unsettling mystery waiting for us in the dark? Our journey begins not with a star, but with an absence, a direction. For decades, astronomers have noticed something profoundly unsettling. Our galaxy, along with every other galaxy in our local neighborhood, is being pulled, not in a random drift, but in a coordinated, relentless rush toward a single point in the distant cosmos. This is the Great Attractor, and it is the first strange object on our list because it redefines our place in the universe. We are not floating freely. We are caught in a current. The source of this immense gravitational pull lies roughly 250 million light-years away, in the general direction of the Centaurus constellation. But here is the catch, the reason it remained hidden for so long. To see it, we must look directly through the crowded, dusty plain of our own Milky Way. Astronomers call this region the zone of avoidance. It is a thick band of gas, dust, and stars that blocks our view like a cosmic blindfold, rendering a huge portion of the extragalactic universe invisible to traditional telescopes. The Great Attractor lurks behind this veil, a shadowy titan we can feel but not clearly see. So what could possibly possess the strength to tug on hundreds of galaxies, including our own? The force required is staggering, implying a concentration of mass tens of thousands of times greater than the Milky Way. Initial theories suggested it might be a previously unknown supercluster of galaxies, an immense gathering of matter. But as our observations improved, peering as best we could through the dust, we found that while there is a large cluster there, it alone does not account for the full strength of the pull. This leads to the heart of the mystery. Is the Great Attractor powered by an even vaster, darker structure? Could it be a focal point of dark matter, a river of invisible mass flowing through the cosmos? Or is it merely a signpost pointing toward something even larger and more distant, pulling everything toward it? The quest to solve this is driving the next generation of astronomy. Instruments like the upcoming Square Kilometre Array, or SKA, telescope are designed to see the universe in radio waves, which can penetrate the obscuring dust of the zone of avoidance. It is like giving cosmic detectives an X-ray vision. By mapping the motions of hydrogen gas in galaxies behind the dust, we hope to finally illuminate the architecture of this gravitational anomaly. The Great Attractor is more than a destination. It is a question written in the motion of the stars, a reminder that even the grand trajectory of our galaxy is dictated by forces we are still struggling to see. That immense pull toward the Great Attractor is not the only invisible force shaping our galaxy's atmosphere. If we could see the sky in gamma rays, the highest energy form of light, the Milky Way would wear a colossal hourglass. Emerging from the very heart of the galaxy, stretching 25,000 light-years both north and south of the galactic plane, are two vast, faintly glowing lobes. These are the Fermi bubbles, and they are the second strange object in our catalogue, a pair of cosmic ghosts haunting our galactic core. They were discovered only in 2010, not by peering through an eyepiece, but by painstakingly analyzing data from the Fermi Gamma Ray Space Telescope. The mission's goal was to map the gamma-ray sky, and in doing so, it revealed this enormous structure that had been hiding in plain sight, or rather, in plain energy for millions of years. The bubbles are not solid. They are immense cavities carved out of the galaxy's own halo gas, filled with a soup of ultra-high-energy particles and magnetic fields. Their edges are sharp and distinct like the shell of a soap bubble, suggesting they were created by a sudden, violent event. But what event? The leading suspect sits right at the base of these bubbles, the supermassive black hole at our galaxy's center, Sagittarius, a star. One theory proposes that several million years ago, Sagittarius, a star, experienced a dramatic feeding frenzy, devouring a massive cloud of gas or even a star. This feast would have unleashed a titanic bipolar jet of energy, punching through the galactic medium and inflating these colossal lobes. Another possibility points to a frenzy of a different kind, a period of intense star formation in the galactic center. If hundreds of massive stars were born and then died in spectacular supernova around the same time, their combined stellar winds and explosions could have blown this giant bubble. There is even a more cataclysmic idea that the bubbles are the final echo of a dwarf galaxy being torn apart and consumed by the Milky Way, its gas splashing upward to form these structures. Regardless of their origin, the scale is almost impossible to grasp. From our vantage point inside the galaxy, each bubble spans half the visible night sky. They are a fossil record of a galactic-scale temper tantrum, a reminder that the quiet center we observe today was once a place of unimaginable violence. The particles trapped inside them are still screaming their story in the language of gamma rays, a faint but persistent whisper of a time when our galactic heart roared. The colossal Fermi bubbles are a testament to violent outbursts, but what if the strangeness lies not in an explosion of matter, but in its profound and eerie absence? Drifting near the edge of our galactic neighborhood is a cosmic desert so vast it defies belief. This is the Boötes void, and its emptiness stretches the limits of our understanding. While it exists beyond the Milky Way, its scale is so immense and its mystery so fundamental that its shadow touches our entire conception of the cosmos. Picture a sphere of space 330 million light-years wide. Within that unimaginable volume, you would expect to find thousands, even tens of thousands of galaxies, based on the average density of the universe. Instead, the Boötes void contains only a few dozen. It is a staggering nothingness, a hole in the cosmic web where the universe seems to have forgotten to place its stars. Our own Milky Way galaxy resides relatively close to this void's frontier, placing us near the shore of this ocean of emptiness. The profound mystery is simple: why is it there? According to the standard model of cosmology, the universe should be roughly uniform on the largest scales, a principle called homogeneity. Matter should be distributed like a froth, with clusters and filaments, but not with gaps of this magnitude. The Boötes void is not just a slightly emptier patch, it is a gaping chasm that challenges that very idea of uniformity. So what could have carved out such a vacancy? One compelling theory suggests it is not truly empty but dark. Perhaps dozens of galaxy clusters long ago merged into a single, unimaginably massive supercluster at the void's core, pulling all surrounding matter inward and leaving this vast hinterland barren. We simply cannot see that central mass because it is shrouded in dust or composed of dark matter. Another, more unsettling idea is that the void is a statistical fluke, a natural but extremely rare low-density bubble in the grand foam of the cosmos. If this is true, it means we live adjacent to one of the universe's most exceptional and lonely places purely by chance. There is even speculation that such voids could be the imprint of collisions with other universes in the multiverse, a scar on the fabric of our reality. Standing at the edge of this nothingness forces a humbling perspective. The vibrant tapestry of galaxies we call home is not the whole story. The universe is also defined by its deserts, by vast tracts of silent darkness where the lights have simply never switched on. The Boötes void asks us a fundamental question: is its emptiness a clue to a deeper cosmic structure, or simply a reminder that in an infinite universe, even profound nothingness must exist somewhere? From the profound silence of cosmic voids, we now turn to a single, fleeting burst of sound. On a quiet Ohio night in August of 1977, the Big Ear radio telescope, a sprawling mesh of wire and steel, was engaged in its routine survey of the sky. Its purpose was to listen not for stars or galaxies, but for the faint, specific whisper of the hydrogen line, a frequency at 1,420 megahertz that scientists reasoned might be a natural calling card for any advanced civilization trying to signal its existence. For the most part, the data printouts were a monotonous stream of letters and numbers, a record of cosmic static. But on August 15th, the machine recorded something extraordinary. For 72 seconds, the signal strength spiked to a value 30 times louder than the background noise. It appeared, peaked, and then vanished, never to be heard again. When astronomer Jerry Amon reviewed the data printout days later, he was so stunned by its perfect, narrowband characteristics that he circled the alphanumeric sequence and in the margin simply wrote, "Wow." That single word gave the signal its immortal name. The wow signal was not just loud, it was precise. It matched the exact hydrogen line frequency astronomers had predicted for an interstellar beacon, and it came from a direction near the constellation Sagittarius, not far from the galactic center. The telescope's design, with two feed horns that scanned the sky minutes apart, provided a crucial check. The signal only appeared in one horn, confirming it came from space and was not some local interference passing overhead. In that brief window, it fulfilled every criterion for an artificial transmission, yet its one-time nature is the core of the mystery. If it was a message, why was it never repeated? Was it a cosmic flare of a type we do not yet understand, perhaps from a comet or a previously unknown astrophysical event? Could it have been a reflected signal from human technology, a satellite or piece of space debris briefly glinting a terrestrial transmission back to Earth? Decades of follow-up observations pointed at that same patch of sky have heard only silence. The wow signal stands alone, a 72-second enigma that continues to haunt the search for extraterrestrial intelligence. It is the ultimate cosmic tease, a shout from the darkness that left behind no echo, only a profound and unanswered question written in red pen on a sheet of computer paper. That fleeting signal leaves us with a question echoing in the void, but some cosmic conversations are not whispers, they are screams. In the constellation Sagittarius, a different kind of signal beats with metronomic precision. This is the Black Widow pulsar, a stellar vampire engaged in a slow and spectacular act of annihilation. It is a millisecond pulsar, officially known as PSRB 1957+20, and it spins over 600 times every second. That rapid spin is not natural for an old, dense stellar corpse. It gained this dizzying speed by stealing life from its neighbor. The pulsar and a small, cool star are locked in a horrifically close orbit, circling each other every 9 hours. The pulsar's intense gravity relentlessly pulls material from its companion, a process that transfers angular momentum and acts like a cosmic whip, spinning the pulsar faster and faster. But the theft does not stop there. The pulsar is a monster with two weapons. Its powerful magnetic field generates a blistering wind of high-energy particles, and as it spins, it also bathes its companion in an unending torrent of radiation. This double assault is literally cooking the smaller star from the outside, vaporizing its outer layers and blowing them into space. The result is a breathtaking and tragic spectacle. The stolen gas forms a vast, glowing cloud that streams away from the victim star, creating a brilliant comet-like tail that stretches across space. Astronomers can actually see this tail of disintegrating stellar material, a real-time autopsy of a star. The fate of this system is written in its present violence. The pulsar will continue to siphon mass and blast its partner with radiation, gradually eroding it over hundreds of millions of years. Eventually, the companion star will be completely consumed, reduced to a planetary mass cinder, or perhaps utterly destroyed. The Black Widow pulsar will then float alone, a rapidly spinning relic of its cannibalistic past, an isolated millisecond pulsar wearing the ghost of its meal. This is not a collision or a sudden explosion, but a drawn-out, intimate destruction. It shows us that in the darkness of space, some of the most profound violence is a quiet, persistent feast. From the violent intimacy of a stellar vampire, we find a structure of unsettling perfection. Drifting in the constellation Monoceros, the unicorn, is an object that looks less like a cosmic accident and more like a carefully crafted artifact. This is the Red Rectangle Nebula, a glowing hourglass of gas and dust so geometrically precise it seems to defy the chaotic nature of space. At its heart lies a dying binary star system, HD 44179. As these stars enter their final acts, they are shedding their outer layers, but they are not creating a typical, billowing cloud. Instead, they have sculpted something extraordinary, a nebula shaped like a perfect X, with a series of glowing, concentric rungs connecting its arms like the rungs of a cosmic ladder or the strands of a spiderweb caught in starlight. The symmetry is so sharp, so clean, it appears almost artificial. How can a dying star produce such a rigid, architectural form? The leading theory involves a delicate and dynamic celestial ballet. Astronomers believe the central star is emitting powerful jets of gas from its poles, but these jets are not stable. They wobble or precess like a slowing top. Imagine holding a spinning garden hose, the stream of water tracing a cone shape in the air. Now place a thick donut of dust around the star's middle, a structure called a torus. As the star's precessing jets slam into this dense dust ring, they are funneled outward, carving out two opposing cones. Over thousands of years, the wobble of the jets paints those cones with successive shells of gas, creating the nebula's distinctive rung-like structure. We are seeing a time-lapse sculpture, each rung a fossilized record of where the jet was pointed in a different century. But the red rectangle's strangeness does not end with its shape. Its deep crimson glow, which gives it its name, comes from a type of light emission seen in certain complex organic molecules. Specifically, scientists have detected signatures of polycyclic aromatic hydrocarbons, large carbon-based molecules that are considered fundamental building blocks for more complex chemistry, even the chemistry of life. Here, in this geometrically perfect tomb of a star system, we are finding the very ingredients that, under different circumstances, could lead to planets and biology. It is a profound reminder that the seeds of complexity, and perhaps even life itself, are being forged in the most unexpected of places, in the precise, beautiful death throes of distant suns. The perfect geometry of the red rectangle gives way to pure chaos at the very heart of our galaxy. Here, orbiting the supermassive black hole Sagittarius, a star, is a tangled forest of mysteries. Among the most persistent are the galactic center filaments, hundreds of long, slender threads that glow with radio light. Discovered in the 1980s, these structures defy simple explanation. Each filament is a cosmic rope, a magnetized tube of high-energy particles stretching up to 150 light-years through space. Yet they are astonishingly thin, only a few light-years across, making them some of the most elongated objects ever detected. They hang in the galactic core like wires in a vast, abandoned switchboard, and they all share one eerily consistent trait. Despite the turbulent maelstrom of forces around the central black hole, these filaments are not randomly scattered. They are aligned almost in unison, perpendicular to the flat plane of the Milky Way. It is as if a giant cosmic comb has been dragged through the galaxy's heart, leaving these orderly strands in its wake. This alignment is the first major clue and the first major puzzle. What force could possibly create and organize such immense structures in the most violent neighborhood of the galaxy? One compelling theory points directly to the central black hole. Perhaps these filaments are scars, fossilized remnants of immense jets that erupted from Sagittarius, a star in the distant past. As those jets punched out of the galactic plane, they could have stretched and magnetized clouds of gas, leaving behind these luminous trails. Another idea suggests they are cosmic strings, hypothetical one-dimensional defects in the fabric of space-time left over from the Big Bang. If such strings exist, they could generate intense magnetic fields as they move, lighting up the surrounding gas. A third possibility is more dynamic. Could these filaments be the wakes left by moving objects? Imagine dense gas clouds plowing through a magnetized medium at the galactic center, their motion creating a glowing trail behind them, like the luminous streak of a meteor in Earth's atmosphere. The trouble is, no single theory perfectly fits all the observations. Their uniform alignment argues for a large-scale, organized event like a black hole outburst. But their varied lengths and distributions suggest a more local, ongoing process. For decades, astronomers have studied them, mapping their intricate web with ever more sensitive radio telescopes. Each new observation adds detail, but not clarity. They remain one of the top unsolved riddles of the Milky Way, a stark reminder that even as we peer into the chaotic core of our galaxy, we are still learning to see the strange architecture hidden within the storm. If those orderly filaments are the galaxy's forgotten wiring, then the next object is a jewel set in a cage of pure force. Orbiting the millisecond pulsar PSRJ 1719-1438 is a world that defies every notion of a planet. Astronomers call it PSRJ 1719-1438b, but its story has earned it a far more captivating name, the Diamond Planet. This is not a rocky world like Earth or a gas giant like Jupiter. Based on its measured mass and the extreme environment it endures, scientists are confident it is the crystalline heart of a murdered star. Billions of years ago, this system likely contained two normal stars. The more massive one exploded, leaving behind the dense, spinning pulsar we see today. Its companion, a white dwarf star made mostly of carbon and oxygen, was then drawn into a horrifically close orbit. Over eons, the pulsar's gravity acted like a cosmic siphoning straw, relentlessly stripping away the white dwarf's outer layers of hydrogen and helium. What remained was an exposed stellar core, a ball of crystallized carbon under unimaginable pressure. This is the planet we detect today, a world with a mass slightly greater than Jupiter's, yet compressed into an object only about 1/5 of Earth's size. That density is the key to its extraordinary nature. Under the crushing gravitational grip of its own mass and the pulsar's immense pull, the carbon atoms have been forced into a rigid, orderly lattice. The entire world is, in essence, a single planet-sized gemstone. Its composition and conditions make it the ultimate form of carbon, a diamond of truly astronomical proportions. The dynamics of its orbit underscore the violence of its creation. This crystallized remnant whips around its pulsar host in just over 2 hours. To put that in perspective, a full year on this world, one complete orbit, is shorter than a single afternoon on Earth. It exists in a perpetual, dizzying sprint, forever circling the stellar corpse that both created and now torments it. The Diamond Planet is more than a cosmic curiosity. It is a direct window into the most extreme outcomes of stellar evolution, a demonstration that under the right conditions of heat, pressure, and theft, the universe can forge wonders of terrifying beauty. It asks us to reconsider what a planet can be, revealing that some worlds are not born, but forged in the aftermath of stellar catastrophe. Our galaxy is not a solitary island, but a predator. The Milky Way's history is written in the stellar debris of its conquests, and one of its meals is still on the cosmic table. This is the Sagittarius dwarf spheroidal galaxy, a small satellite galaxy caught in a death spiral. For billions of years, it has been orbiting our own, and with each pass, the Milky Way's immense gravity has been peeling it apart, star by star. We are witnessing a slow-motion act of galactic cannibalism, a process that is teaching us how galaxies like ours grow. The primary evidence is not a single cohesive object anymore, but a ghostly river of stars. As the dwarf galaxy is stretched and torn, its stars are not instantly absorbed. Instead, they are pulled into long, looping ribbons that wrap around the Milky Way like the strands of a celestial spiderweb. Astronomers call this the Sagittarius Stream, and it is one of the largest and most distinct structures in our galactic halo. It is a fossilized record of the dwarf galaxy's orbit, a shimmering trail of breadcrumbs left behind from its repeated passages through the galactic plane. By mapping the positions and motions of these stream stars, scientists can rewind the cosmic clock. They can trace the stream's path backward, reconstructing the dwarf galaxy's original orbit and determining how many times it has already swung around the Milky Way. This is galactic archaeology, using the debris of a destroyed neighbor to read our own galaxy's violent past. The story it tells is dramatic. The Sagittarius dwarf was once a much larger, more substantial galaxy. Each close encounter with the Milky Way has stripped away its outer stars and gas, leaving behind the dense, resilient core we see today, which is now on its final orbits. Within the next 100 million years, this core will likely be completely disrupted, its stars scattered into the Milky Way's halo, becoming indistinguishable from our galaxy's native population. This ongoing merger is more than a historical lesson. It is a preview of the future. The same gravitational forces that are slowly dissolving the Sagittarius dwarf are at work on a far grander scale. Our Milky Way and the neighboring Andromeda galaxy are on a collision course pulled together by their mutual gravity. In about 4.5 billion years, they will begin a similar, though far more colossal, dance of destruction and merger. The serene spiral structures of both galaxies will be stretched and shredded, their stars flung into new, chaotic orbits, eventually coalescing into a single, giant elliptical galaxy. The Sagittarius Stream is a small-scale rehearsal for that ultimate cosmic event. It shows us in real time the fundamental truth that galaxies are not static islands, but dynamic creatures that grow by consuming others, forever reshaping themselves in the dark ocean of space. The slow, gravitational digestion of a dwarf galaxy is one way stars are scattered, but some stars are not merely drifting away, they are violently ejected. Racing through the halo of the Milky Way are celestial projectiles known as hypervelocity stars. These are not just fast, they are impossibly fast, traveling at speeds exceeding 1,000 kilometers per second, fast enough to cross the entire United States in less than 5 seconds. At that velocity, they are not orbiting the galaxy, they are escaping it entirely on a one-way journey into the endless dark of intergalactic space. The most famous of these cosmic fugitives is a star designated S5HVS1, discovered streaking through the constellation Grus, the Crane. Its trajectory is the key to its origin. By tracing its path backward across the sky, astronomers found its line of flight points like a perfectly drawn arrow directly back to the galactic center, to the supermassive black hole Sagittarius, a star. This is not a coincidence, it is a signature. The leading theory for how a star gains such incredible speed involves a celestial slingshot of terrifying elegance. Imagine a binary star system, two stars orbiting each other, drifting too close to the black hole's immense gravitational well. In a gravitational three-body interaction, one star can be captured by the black hole, falling into a tight orbit. The conservation of energy and momentum demands a dramatic counterbalance, so the other star is flung away at a staggering velocity, like a stone from a sling. The captured star becomes a prisoner of the black hole, while its partner is ejected at a speed that can exceed the Milky Way's own escape velocity. S5HVS1 is that ejected partner, a solitary sun screaming away from the scene of a cosmic crime. Its fate is now sealed. It will continue on its hyperbolic trajectory, leaving the gravitational pull of our galaxy behind forever. In millions of years, it will be a lonely traveler in the void between galaxies, a ghost of a stellar partnership shattered by a monster's gravity. The existence of these runaway stars does more than showcase galactic violence. It provides a unique probe. By studying their speed and composition, astronomers can learn about the environment at the very heart of the Milky Way and test the properties of the black hole itself. Each hypervelocity star is a message in a bottle hurled from the galactic core, telling the story of a close encounter with oblivion. While hypervelocity stars are flung out by the immense gravity of the galactic core, that same force is not the only thing holding our galaxy together. In fact, the gravity we can see from all the stars, gas, and dust is only a fraction of the story. The Milky Way is embedded in something far more massive and profoundly strange, an immense, invisible sphere that dictates the motion of everything within it. This is our galaxy's dark matter halo, and it is the single most dominant, yet completely unseen, object on our list. We know it exists not because we can see it, but because without it, our galaxy would simply fly apart. The evidence emerged from a simple, fundamental measurement: how stars orbit the galactic center. According to the laws of gravity, stars farther from the center should move more slowly, just as Pluto orbits the Sun much slower than Mercury. But when astronomers measured the rotation speeds of stars and gas clouds in the Milky Way's outer regions, they found something shocking. These distant objects were moving just as fast as stars closer in. The entire outer disk of the galaxy was rotating at a near-constant, breakneck speed. The only possible explanation was that there had to be far more mass out there, mass we could not see, providing the extra gravitational glue to keep those stars from being flung into the void. This unseen mass forms a vast spherical halo enveloping the entire luminous disk of the Milky Way. We can also detect its presence through a phenomenon called gravitational lensing. When light from a distant galaxy passes near this halo, the dark matter's gravity bends the light's path like a lens, distorting and magnifying the background galaxy's image. By mapping these subtle distortions, astronomers can literally trace the outline of the invisible, creating a shadow map of the dark matter's distribution. The scale of this halo is staggering. It contains roughly 5 times more mass than all the ordinary matter in the galaxy combined. It is the unseen skeleton upon which the Milky Way is built, the hidden framework that determines how galaxies form and cluster together. And here lies the ultimate mystery. After decades of searching, we still have no definitive idea what it is. We have ruled out dim stars, rogue planets, and cold gas. The leading candidate is a hypothetical, as yet undetected particle that interacts only through gravity and perhaps the weak nuclear force, making it nearly impossible to snare in a laboratory. Other, more exotic ideas suggest the effect we call dark matter is not matter at all, but a sign that our understanding of gravity itself is incomplete on cosmic scales. This invisible halo is not a passive backdrop, it is the primary actor in our galaxy's destiny. It governs how stars move, it guides the mergers of satellite galaxies like the Sagittarius dwarf, and its gravitational pull is what initially draws in the gas that forms new stars. Every structure we see is dancing to the tune of this silent, unseen conductor. The dark matter halo is the ultimate strange object, a ghostly presence we can measure with precision but cannot touch, a defining mystery that whispers to us through the very motion of the stars. That invisible halo of dark matter dictates the grand architecture of our galaxy, but within its luminous disk, individual stars write their own final chapters in spectacular detail. One of the most stunning of these finales is the Cat's Eye Nebula. Glowing in the constellation Draco, this is the death shroud of a sun-like star, and its intricate structure tells a story of violent, repeated outbursts. When a star like our own Sun exhausts its nuclear fuel, it does not go quietly. It swells into a red giant, then sheds its outer layers in a series of convulsive heaves. The hot, exposed core then floods this ejected gas with ultraviolet radiation, causing it to glow for a few fleeting millennia. We call such an object a planetary nebula, though it has nothing to do with planets. The cat's eye, however, is no simple bubble. Hubble Space Telescope images reveal an astonishingly complex sculpture of gas. At its heart is a brilliant, elliptical ring like a cosmic eye. Surrounding it are at least 11 concentric shells of gas, each a perfect bubble nestled within the next, like the layers of a celestial onion. Extending from the poles are immense, jet-like structures that blast outward for trillions of miles, creating symmetrical loops and knots. This intricate geometry is a fossil record. It suggests the central star did not shed its skin in one smooth event, but in a series of powerful, episodic outbursts. Every few thousand years, the star experienced a violent pulse, ejecting a new shell of material. The cause of these fits and starts is still debated, but it may involve the star's final, desperate attempts to fuse new elements in its core, each attempt triggering a new eruption. The engine of this beautiful chaos is the nebula's central star itself, one of the hottest objects known in our galaxy. With a surface temperature estimated at nearly 400,000 degrees Fahrenheit, it is over 60 times hotter than our Sun. This tiny, white-hot stellar cinder is the reason the entire nebula glows, its intense radiation exciting the atoms in the expelled gas. The cat's eye is a temporary masterpiece. In perhaps 10,000 years, the central star will cool, the ultraviolet light will fade, and the glorious gas clouds will dissipate into the interstellar medium, their atoms destined to be recycled into new stars and planets. For now, it hangs in space as a perfect cosmic snapshot, a layered chronicle of a star's final, gasping breaths. The intricate death of a star like the cat's eye leaves behind a dense, hot cinder, but some stellar corpses are born under far more extreme pressure. Drifting in the darkness not far from Earth in galactic terms are 7 solitary enigmas. Astronomers call them the Magnificent Seven, and they are neutron stars unlike any others we have found. Each one is the collapsed core of a massive star that went supernova, compressed into a sphere only about 12 miles across yet weighing more than our Sun. They possess the density of an atomic nucleus, where a single sugar cube-sized piece would weigh as much as a mountain. But what makes these 7 so strange is what they lack. They are not pulsars sending out lighthouse beams of radiation as they spin. They have no binary companions to steal from or heat them. They are utterly alone, and they should be dark and cold. Yet they glow. These isolated neutron stars shine brightly in X-rays, the high-energy light that reveals the hottest and most violent processes in the universe. Their brilliance comes from the residual heat of their catastrophic birth, a supernova explosion so ferocious that it left the core glowing like a cosmic ember at nearly 1,000,000 degrees. We are catching them in a brief cosmic moment, slowly cooling over hundreds of thousands of years. But their light holds a deeper puzzle. When scientists analyze the specific signature of their X-ray emission, the spectra, it does not match what our models predict. A neutron star of this age should have a thin atmosphere of hydrogen or helium, its light smoothed by the intense gravity into a predictable curve. The light from the Magnificent Seven shows distinct absorption features, sharp dips in their spectra that suggest something far more exotic is at play. One compelling theory is that their surfaces are not gaseous at all, but solid. The unimaginable pressure at their surface, billions of times stronger than Earth's atmosphere, could have forced their material to crystallize into a rigid lattice, a crust of iron nuclei organized into a perfect, unearthly solid. The observed absorption lines could be the fingerprint of vibrations within this iron crystal surface. Another, even more speculative idea involves an atmosphere not of light elements, but of heavier, exotic particles. In such intense magnetic and gravitational environments, atoms themselves are stretched into long, needle-like shapes, creating a kind of atmosphere unlike any chemistry we know. These 7 objects are, in effect, natural laboratories for states of matter that cannot exist on Earth. They present us with a profound challenge to understand the physics of a world where a teaspoon of material defies our everyday experience, and where the surface itself may be a single, perfect crystal spanning dozens of miles. They are silent, cooling relics, but their faint X-ray whispers are forcing us to rewrite the book on the most extreme matter in the cosmos. The silent, crystalline surfaces of the Magnificent Seven are the ultimate in stellar isolation, but our galaxy also hosts wanderers of a very different kind. Drifting toward us is a ghost, a colossal and silent structure known as the Smith Cloud. This is no faint nebula, but a titanic river of hydrogen gas over 11,000 light-years long and 2,500 light-years wide. If it were visible to the naked eye, it would stretch across 30 degrees of the night sky, an immense dark spear aimed directly at the Milky Way's disk. Discovered in the 1960s by astronomy student Gail Smith using radio telescopes, this cloud is not merely floating nearby. It is a high-velocity projectile screaming toward us at nearly 200 miles per second. Its trajectory is clear and inevitable. In roughly 30 million years, it will slam into the spiral arm of our galaxy known as the Perseus Arm. The collision will be a spectacle of pure cosmic force, compressing the cloud's vast reservoirs of gas and triggering fireworks on an unimaginable scale. The impact will ignite a furious burst of star formation, lighting up that region of the galaxy with millions of new suns. But the true mystery of the Smith Cloud lies not in its future but in its past. Where did it come from? For decades, astronomers assumed it was a pristine fragment of intergalactic space, a leftover building block from the formation of the local group of galaxies finally falling in. That theory collapsed when the Hubble Space Telescope took a closer look. By analyzing the light from distant quasars shining through the cloud, scientists could measure its chemical composition, its metallicity. They found it was rich in sulfur, an element forged only in the hearts of stars. This was the crucial clue. The Smith Cloud is not a virgin visitor from the void. It is made of material that has already been processed inside stars. It carries the chemical fingerprint of the Milky Way itself. This discovery paints a far more dramatic story. The Smith Cloud is a galactic boomerang. It originated in the outer fringes of our own galaxy, perhaps ripped away by a close gravitational encounter with a dwarf galaxy, or blown out by the combined force of multiple supernova explosions in the galactic disk some 70 million years ago. It was flung out into the galactic halo at tremendous speed, reaching the apex of its trajectory, and now, pulled by the Milky Way's relentless gravity, it is falling back home. We are witnessing the return of a prodigal structure, a piece of our own galaxy coming back to rejoin itself after a cosmic odyssey lasting tens of millions of years. Its impending collision is not an invasion but a homecoming, one that will reshape a part of our galaxy and remind us that even on the largest scales, what goes out must sometimes come back. Those immense Fermi bubbles are a fossilized scream, but what was the actual sound? What specific cataclysm could launch 2 lobes of plasma 25,000 light-years into space? The answer may lie in the concept of galactic geysers, immense jets of energy erupting from the very heart of the Milky Way. To understand them, we must rewind the cosmic clock. The supermassive black hole, Sagittarius A star, is quiet now, but it was not always so. Evidence suggests it has experienced periods of violent activity, feasting on whatever stray gas or stars ventured too close. When a black hole feeds, it does not swallow everything. Some of the infalling material, superheated to millions of degrees, gets channeled by intense magnetic fields and spun up into a swirling disk. From the poles of this disk, the black hole can launch 2 opposing, pencil-thin jets of charged particles moving at nearly the speed of light. These are not gentle streams, they are relativistic blowtorches capable of punching through interstellar gas for incredible distances. Computer simulations tell a compelling story. They show that if Sagittarius, a star, experienced a significant feeding event several million years ago, these bipolar jets could have plowed directly into the thick halo of gas surrounding the galactic disk. The jets would not remain narrow forever. As they rammed into this galactic atmosphere, they would slow down, spread out, and transfer their immense energy to the surrounding material. This process would have inflated two gigantic hot cavities on either side of the galactic plane, exactly where we see the Fermi bubbles today. The sharp edges of the bubbles are like the shock front of a cosmic explosion, the boundary where this ancient jet's energy finally dissipated. Think of it not as a single explosion, but as a sustained eruption. A geyser on Earth erupts when pressure builds and hot water is forced upward. In a similar way, the black hole's accretion disk built up pressure, and the resulting jets forced a torrent of plasma upward and downward for perhaps hundreds of thousands of years. This was not a one-time blast, but a prolonged outburst that sculpted the very shape of our galaxy's atmosphere. The particles inside those bubbles are still seething with that ancient energy, which is why they glow in high-energy gamma rays. This theory transforms the bubbles from a static mystery into a dynamic story. They become the lingering echo of a time when our galactic center was an active galactic nucleus, a quasar in miniature. It suggests our quiet neighborhood was once the site of a brilliant and violent spectacle, a testament to the fact that even the most massive objects in the universe have dormant periods punctuated by episodes of terrifying power. That ancient geyser left its mark in the form of the Fermi bubbles, but the environment around Sagittarius, a star, is far from settled. It remains a cosmic laboratory where even our best predictions can shatter against reality. This brings us to a more recent drama that unfolded right before our telescopes, the strange case of Object G2. In 2011, astronomers tracking the chaotic dance of stars around the galactic center spotted something new. A faint, elongated blob of dust and gas was on a collision course, or rather, a very close encounter with the supermassive black hole itself. Predictions were made with great excitement. This object, dubbed G2, was calculated to make its closest approach in early 2014. Based on its appearance and trajectory, scientists believed it was a simple cloud of hydrogen gas, perhaps ripped from a larger nebula. The expectation was a spectacular cosmic show. As it neared the black hole's immense tidal forces, the cloud should have been stretched, shredded, and torn apart like cotton candy in a hurricane. This violent process would have superheated the gas, causing it to glow brightly in infrared and X-ray light, offering a rare front row seat to the feeding mechanics of a black hole. The entire astronomical community watched, instruments poised, but G2 did not cooperate. It made its swing around the black hole, passing within just 260 times the distance between Earth and the Sun, a hair's breadth in galactic terms. It was stretched and distorted by the gravity, yes, but it did not disintegrate. It did not light up the sky with a brilliant flare. Instead, it survived the encounter largely intact, emerging on the other side in a shape that suggested something more cohesive, more durable than a wispy cloud. The black hole's feast, it seemed, was cancelled. This survival forced a complete rethink. The leading theory now suggests G2 is not just a cloud. It is likely a star, but a star concealed within an immense, extended cloak of its own making. The idea is that G2 is the product of a stellar merger, where two stars, likely binary partners, spiraled together and coalesced into a single, larger star. This violent merger would have ejected a vast shroud of gas and dust, which then cooled and obscured the central star from our view. What we were seeing was not a doomed cloud, but the dusty cocoon of a reborn star, massive and resilient enough to hold itself together against the black hole's pull. Another possibility is that it is a single, massive star with an extraordinarily powerful stellar wind, continuously puffing out a dense, extended atmosphere that mimics a cloud. In either case, the object's compact core provided the gravitational anchor that kept it from completely dissipating. The G2 event taught us a humbling lesson about the dynamic zoo of objects that can exist in such an extreme environment. It revealed that the galactic center is not just a place of destruction, but also of transformation where stars can collide, merge, and wrap themselves in veils of their own debris, creating phantom clouds that defy our first impressions. The survival of G2 underscores a fundamental truth near a black hole: nothing is ever as simple or as fragile as it seems. The galactic center is a place of both violent destruction and strange rebirth, and that theme of stellar transformation echoes far beyond the black hole's shadow. In the quiet, ancient globular clusters that orbit the Milky Way, we find stars that are living a cosmic lie. These are the blue stragglers, and they are brilliant, hot, blue stars shining defiantly in stellar neighborhoods where they simply should not exist. Globular clusters are among the oldest structures in the galaxy, dense balls of hundreds of thousands of stars, all born from the same primordial gas cloud roughly 10 billion years ago. In such a retirement community, every star should have aged gracefully together. The massive, hot blue stars should have burned out billions of years ago in spectacular supernova, leaving behind only cooler, redder, lower-mass stars. Yet when we look at these clusters, we spot these vibrant blue interlopers, stars that appear far too young and energetic for their surroundings. It is as if we walked into a room full of centenarians and found a group of vibrant 30-year-olds. How can a star cheat time? Astronomers have focused on two compelling and equally dramatic theories. The first is a story of stellar collision and merger. Globular clusters are incredibly crowded places, with stars whizzing past each other at tremendous speeds. In this dense stellar traffic, close encounters and direct collisions, while still rare, become possible over billions of years. Imagine two aging, lower-mass stars slamming into one another. Their cores could merge, creating a single, more massive star. This new, more massive object would burn hotter and bluer, effectively resetting its evolutionary clock. It is not truly young, but it is a Frankenstein's monster of stellar parts, a composite being that shines with a deceptive, borrowed youth. The second theory involves a slower, more intimate form of theft within binary star systems. In a close pair, one star may expand as it ages, beginning to dump its outer layers onto its companion. This transfer of mass can fundamentally change the recipient star. It gains fresh hydrogen fuel for its core, becoming more massive and hotter, while the donor star is stripped down to its bare core. The recipient is thus rejuvenated, transformed into a blue straggler, while its partner becomes a faded stellar ghost. Both scenarios are acts of stellar vampirism or cannibalism, pathways to a second life granted not by nature but by violent interaction. These blue stragglers are not breaking the laws of physics, they are exploiting a loophole. They prove that in the dense stellar cities of globular clusters, stars are not isolated islands. Their lives are intertwined, their fates can merge, and their apparent age can be a beautiful, brilliant illusion. They stand as a testament to the fact that in the cosmos, youth is not always a matter of birth, but sometimes a prize won through collision or cosmic partnership. Blue stragglers prove stars can steal a second life, but entire galaxies can be sculpted into forms of breathtaking perfection. On the fringes of our cosmic neighborhood floats a galaxy that seems more like a celestial bullseye. Catalogued as PGC 10000714, this is a ring galaxy, a type so rare it feels like a glitch in the universe's design. At its heart sits a perfectly round, ancient core of old, reddish stars. Separated by a stark, dark gap of near emptiness, a brilliant, circular ring of young, hot blue stars orbits at a respectful distance. The two components are perfectly aligned, concentric circles of stellar fire divided by a cosmic moat. It is a structure of such precise geometry it appears almost artificial, a cosmic mandala painted against the dark canvas of space. This galaxy is a close cousin to the famous Hoag's object, another pristine ring galaxy, and its existence challenges our understanding of galactic evolution. How does a galaxy avoid the messy spiral arms or the chaotic elliptical shape to become this perfect two-part sculpture? Astronomers are piecing together several violent yet elegant origin stories. The most dramatic theory involves a head-on galactic collision. Imagine a small, compact galaxy, perhaps a dwarf galaxy, plunging directly through the center of a larger disk galaxy, like a bullet through a bullseye. The gravitational shockwave from this collision would ripple outward through the larger galaxy's disk, compressing gas and dust as it travels. This compression wave triggers a frenzy of star formation in a perfect circle, leaving the older central core relatively undisturbed but now isolated. The intruder galaxy, having delivered its destructive message, would continue on its way, leaving behind this beautiful, ringing artifact. Another possibility points to a massive internal instability. A central bar of stars common in spiral galaxies could become unstable over time, funneling gas outward to a resonant radius where it accumulates and ignites into a ring of new stars. The bar itself might then fade, leaving only the core and the ring. A third idea suggests the ring is not born from the core at all, but adopted. A dwarf galaxy rich in gas could have been captured and torn apart by the larger galaxy's gravity. Its material spread into a circular orbit that then coalesced into the brilliant blue stars we see. Regardless of the precise mechanism, the result is a galaxy frozen in a moment of both violence and perfect order. The dark gap between the core and the ring is not truly empty. It is a cemetery of older, fainter stars and quiet gas, a buffer zone between two distinct eras of stellar life. This celestial oddity forces us to confront the artistry hidden within cosmic chaos, where catastrophic events can sometimes write their signatures in circles of brilliant light. The artistry of ring galaxies is born from collision, but some stars are collisions waiting to happen. Among the most volatile objects in the Milky Way are the luminous blue variables, hypergiant stars so massive and unstable they are essentially walking stellar earthquakes. These are not ordinary stars, they are cosmic pressure cookers, balancing on a knife's edge between shining brilliantly and tearing themselves apart. Their lives are measured not in steady billions of years, but in violent, eruptive fits that can reshape their surroundings in a single human lifetime. The prime example of this terrifying instability is not a distant abstraction, but a resident of our own galaxy, Eta Carinii. Located about 7,500 light-years away in the constellation Carina, this star is a monster. It is a binary system where the primary star is estimated to be over 100 times the mass of our Sun, shining with the power of 5 million suns. For most of recorded history, Eta Carinii was a modest star, barely visible. Then, in the 1840s, it underwent a cataclysmic event known as the Great Eruption. Over the course of about 20 years, it became the second brightest star in the entire night sky, outshone only by Sirius despite its immense distance. Astronomers of the time without modern telescopes could only watch in awe as it flared. We now know what happened. The star did not explode in a supernova, it suffered a gigantic stellar tantrum. It ejected an enormous amount of its own mass, at least 10 times the mass of our Sun, in two opposing bipolar jets. That ejected material did not just drift away. It slammed into slower-moving gas the star had shed earlier, creating a spectacular, expanding nebula. Today, we see that nebula as the homunculus, a twin-lobed cloud of gas and dust that looks like a cosmic butterfly or an hourglass, glowing from the reflected light of the hidden, furious star within. The homunculus is a fossil of that single, violent episode, a time capsule from the 1840s traveling outward at millions of miles per hour. But Eta Carinii is not done. It remains highly unstable, prone to smaller eruptions and wild swings in brightness. Luminous blue variables like it are defined by this extreme instability. Their immense gravity struggles to hold onto their own outer layers, which are being pushed outward by the ferocious radiation pressure from within. This creates a constant, violent tug of war. The star may puff up to a tremendous size, becoming cooler and redder, before suddenly contracting and heating up again, shedding shells of material in the process. They are the ultimate ticking time bombs. Their fate is sealed by their own mass. When a star this large finally exhausts its nuclear fuel, its core will collapse not into a neutron star, but directly into a black hole. The resulting explosion is not a typical supernova. It is a hypernova, an explosion orders of magnitude more energetic, potentially accompanied by a gamma-ray burst, the most luminous electromagnetic events known in the universe. A gamma-ray burst directed at Earth from within our galaxy would be a catastrophic event capable of stripping away the ozone layer and triggering a mass extinction. Eta Carinae is pointed away from us, a small mercy in the grand scheme. These stars are the galaxy's ultimate agents of change. Their violent lives and spectacular deaths seed the interstellar medium with heavy elements, and their final blasts can sterilize regions of space or, conversely, trigger new waves of star formation by compressing nearby gas clouds. To observe a luminous blue variable is to watch a star living on borrowed time, a brilliant, trembling giant whose final act will be a cosmic event of unimaginable scale. Our galaxy's most brilliant and unstable stars are governed by a larger, hidden architecture. For centuries, we pictured the Milky Way as a simple, elegant spiral, like a pinwheel of starlight. But modern astronomy has revealed a different truth. Our home is a barred spiral galaxy. At its very heart lies a dense, elongated structure made of billions of stars, a colossal galactic bar spanning over 27,000 light-years. This is not a static shape, but a dynamic, rotating engine that orchestrates the motion of the inner galaxy. Imagine the bar not as a rigid rod, but as a swirling, stellar traffic jam. Its immense gravitational field acts like a cosmic shepherd, guiding the orbits of stars and gas clouds. Material does not simply fall inward toward the central black hole. Instead, it follows the bar's gravitational contours, streaming along its leading edges in great rivers of gas and stars before being funneled toward the galactic center. This process creates what astronomers call stellar and gas dynamical resonances, regions where orbits sync up with the bar's rotation, piling up material into the prominent spiral arms we see. The bar itself rotates as a solid-like structure, though it is made of countless individual stars. Its rotation drives a fundamental rhythm throughout the inner Milky Way, influencing everything from when new stars are born to how gas eventually feeds Sagittarius, a star. Without this central bar, our galaxy's core would be a very different place, likely quieter and less structured. Its presence explains why the inner regions are so rich in star formation and why we observe certain patterns in the motion of stars that would otherwise seem chaotic. This grand structure also solves an old puzzle. For a long time, observations suggested the Milky Way's central regions were asymmetrical, with more stars on one side than the other. The bar provides the explanation. From our position within the disk, we are looking at this giant structure at an angle, giving us an off-center and lopsided view of our own galactic heart. So the Milky Way's bar is more than a shape. It is the central dynamo of our home, a strange object defined not by its alien composition, but by its sheer gravitational influence, sculpting the destiny of stars and gas on a scale so vast we are only just beginning to map its full effects. That immense, rotating bar of stars is a relatively recent development in the life of our galaxy, but some stars remember a time before any such structure existed. Drifting through the galactic halo, a lonely traveler holds a secret in its ancient light. This is the Methuselah star, officially catalogued as HD 140283, and it is the oldest known individual star within our celestial neighborhood. Its light, a faint whisper from over 190 light-years away, carries a chemical story from the dawn of time. This star is a subgiant, a sun that has exhausted the hydrogen in its core and is beginning its transition toward the end of its life. But its true distinction is its age, estimated at approximately 13.7 billion years. That means it formed when the universe itself was in its cosmic infancy, a mere few 100 million years after the Big Bang. We know its incredible age not from a birth certificate but from its profound poverty. The Methuselah star is extremely metal-poor. In astronomy, metals refer to any element heavier than hydrogen or helium. These heavier elements, like carbon, oxygen, and iron, are forged in the cores of stars and scattered by their explosive deaths. A star born from the primordial gas of the early universe would contain almost none of these metals, as there had been no previous generations of stars to create and distribute them. The Methuselah star's composition is exactly that, a ghostly fingerprint of a nearly pure hydrogen and helium cosmos. Its metallicity is less than 1% that of our Sun, marking it as a true relic from the first generation of stellar formation. This age presented astronomers with a fascinating and profound puzzle. Initial, highly precise measurements of the star's distance, brightness, and composition suggested an age of around 14.5 billion years. This created a logical impossibility, a star that appeared to be older than the universe itself, which is estimated at 13.8 billion years. The discrepancy was not a failure of science but a catalyst for refinement. Astronomers re-examined every variable. The key was a more precise measurement of the star's distance achieved by the Hubble Space Telescope. A slight adjustment in distance changed the calculation of its intrinsic brightness, which in turn refined the models of its stellar evolution. Further refinements accounted for the star's exact oxygen content, which influences its opacity and how it burns its fuel. With these improved data points, the estimated age settled comfortably within the universe's timeline at around 13.7 billion years, give or take a few hundred million. This resolution is a triumph of the scientific process. The Methuselah star no longer contradicts the age of the cosmos, it confirms it. It provides a critical, observational lower limit. The universe must be at least as old as the oldest things we find inside it. This ancient wanderer is more than a record holder. It is a direct messenger from the era of first light, a solitary witness to the moment our galaxy was just beginning to coalesce from the dark, pristine clouds of the early cosmos. Deep within the chemical fingerprint of our oldest stars lies a clue to a different kind of ancient relic, one that glows with the energy of annihilation. At the very heart of the Milky Way, astronomers have mapped a mysterious and pervasive fog. This is the galactic center excess, an unexplained glow of gamma-ray light that bathes the inner few hundred light-years of our galaxy. Unlike the sharp, point-like sources of gamma rays from pulsars or black holes, this is a diffuse, almost ethereal emission, a soft hum of high-energy light with no obvious cause. Its discovery came from painstaking analysis of data from the Fermi Gamma Ray Space Telescope, which revealed that after accounting for all known sources, a persistent, unexplained excess remained, centered perfectly on Sagittarius, a star. The distribution of this glow is its first major clue. It forms a roughly spherical halo around the galactic center, fading smoothly with distance. This shape is significant because it matches what theorists predicted for a particular, long-hunted signal, the annihilation of dark matter particles. According to some models, if dark matter particles are their own antimatter counterparts, they could collide and annihilate each other when they meet, converting their mass directly into energy and producing a spray of gamma rays. The dense concentration of dark matter predicted to exist at the galactic center would be the perfect place for such collisions to occur frequently, creating just this kind of smooth, spherical glow. The possibility sent a thrill through the physics community, as it offered a direct way to finally detect the invisible substance that shapes the cosmos. But science thrives on debate, and an alternative explanation soon gained ground. Could this glow instead come from a vast population of unresolved stellar corpses? The leading candidate here is a celestial chorus of thousands of millisecond pulsars, the ancient, rapidly spinning neutron stars we encountered earlier. These faint objects, each individually too dim for Fermi to distinguish at that distance, could collectively produce a gamma-ray fog that, from our vantage point 26,000 light-years away, would blur together into a smooth, diffuse excess. Supporters of this theory point to the fact that we see such pulsars in other parts of the galaxy, and their expected distribution could plausibly mimic the observed signal. The debate remains fierce and unresolved, a classic scientific standoff between an exotic, new physics explanation and a more conventional, if still extraordinary, astrophysical one. Future telescopes with higher resolution in gamma rays may be the final arbiter. If the excess resolves into thousands of pinpoint sources, it will reveal a previously unseen population of ancient stellar zombies. If it remains stubbornly smooth and featureless, the case for dark matter annihilation grows profoundly stronger. The galactic center excess is more than a strange glow. It is a cosmic riddle written in the universe's most energetic language, and its solution will either illuminate the darkest corners of physics or reveal a hidden city of the dead at the very heart of our home. That mysterious gamma-ray glow at the galactic center speaks in a whisper, but in April of 2020, the cosmos shouted. A brilliant millisecond flash of radio light erupted from within our own galaxy, a signal so powerful it was detected from over 30,000 light-years away. This was FRB 200428, the first fast radio burst ever traced to a known source inside the Milky Way. For over a decade, astronomers had catalogued these bizarre events, fleeting blasts of radio energy from galaxies billions of light-years distant. Each one released more energy in 1,000th of a second than our Sun emits in 3 days, yet their origins were a complete mystery, hidden in the unimaginable depths of intergalactic space. This single local burst changed everything. Its origin point was not a mystery. It came from a known object in the constellation Vulpecula, a highly magnetized neutron star called SGR 1935+2154, a magnetar. Magnetars are the universe's ultimate magnets, possessing magnetic fields 1,000 trillion times stronger than Earth's. These fields are so intense they strain the very structure of the star itself, causing starquakes that can crack its solid crust and unleash colossal bursts of X-rays and gamma rays. This particular magnetar had been active and telescopes were watching. On April 28th, it did something unprecedented. It produced not just its usual X-ray flare, but an accompanying, spectacularly bright burst of radio waves. Instruments across the globe and in space caught the event. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, radio telescope in Canada recorded the brilliant radio pulse. Simultaneously, NASA Neil Gehrels Swift Observatory and other spacecraft detected an intense X-ray burst from the exact same spot on the sky at the exact same moment. This coincidence was the smoking gun. For the first time, we had a front-row seat to the engine of a fast radio burst. The data painted a vivid picture of a catastrophic rearrangement of the magnetar's immensely powerful magnetic field. Think of it like a cosmic circuit breaker snapping. The magnetic field lines, twisted and stressed to a breaking point, suddenly reconnect, releasing a catastrophic amount of energy that accelerates particles to near light speed. This generates a shock wave that ripples through the surrounding environment, producing both the flash of X-rays we see and a coherent, lighthouse-like beam of radio waves. If that beam is pointed directly at Earth, we see it as a fast radio burst. This local event was the Rosetta Stone astronomers had been desperate to find. It proved conclusively that at least some fast radio bursts, and likely a great many of them, are born from the violent tantrums of magnetars. The distant extragalactic bursts we had been detecting for years were simply the same phenomenon, viewed from across the cosmic ocean, their signals stretched and weakened by their epic journeys. Yet, even with this monumental discovery, the mystery is not fully solved. The energy released by our galactic magnetar burst was still about 1,000 times less energetic than the most powerful extragalactic fast radio bursts. This tells us that while magnetars are one source, they may not be the only source. Perhaps the most distant bursts come from younger, more ferociously magnetic magnetars, or from even more extreme events like the collision of neutron stars or the final death cries of evaporating black holes. The detection of FRB 200428 transformed a profound cosmic riddle into a tangible, physical process we can now study in our own backyard. It reminds us that sometimes the key to unlocking the universe's grandest secrets arrives not as a whisper from the edge of time, but as a deafening crack of thunder from a familiar neighborhood. That local magnetar burst gave us a key to one mystery, but it also forces us to ask where we are looking from. Our position in the cosmos is not a neutral observation deck. We are embedded within structures that shape our view of everything beyond, and one of those structures might be a staggering emptiness. Astronomers have proposed that our entire local group of galaxies, including the Milky Way, resides inside a colossal bubble of nothingness called the KBC void. This is not a small pocket of space. If confirmed, it would be a spherical region roughly 2 billion light-years across, making the Boötes void we discussed earlier seem like a small pothole by comparison. We are not at its edge, but astonishingly close to its very center. This idea emerges from careful mapping of galaxy densities in our cosmic neighborhood. When astronomers count the number of galaxies in all directions, they find a curious deficit. The space around us appears less crowded than the standard cosmological models predict. It is as if we are living in a grand, underpopulated cavity within the larger cosmic foam. The implications of this are profound, touching on one of the foundational pillars of modern cosmology, the cosmological principle. This principle states that on sufficiently large scales, the universe is homogeneous and isotropic, meaning it should look roughly the same in every direction and from every location. A void 2 billion light-years wide, with us at its center, would be a glaring exception to that rule. It would mean we are not in a typical place at all, but in a special, unusually sparse region. This potential bias has direct consequences for how we measure the universe's most fundamental properties. Take the Hubble constant, the rate at which the universe is expanding. We measure this by observing how fast distant galaxies are moving away from us, their redshift. But if we are sitting inside a giant void, the local gravitational environment is different. The relative lack of mass inside the void means there is less gravity pulling on galaxies here, so they might be flowing outward toward the denser walls of the bubble. This extra outward motion could make it appear from our vantage point that the local universe is expanding faster than it truly is on a global scale. Some scientists argue this could explain the persistent and troubling Hubble tension, the discrepancy between measurements of the expansion rate taken from nearby objects versus those inferred from the early universe's afterglow, the cosmic microwave background. If our local measurements are inflated because we are in a void, then the true expansion rate might be more in line with the early universe data. The debate is fierce. Critics point out that a void this large is statistically very unlikely in our standard model of the universe. Proponents counter with the maps, insisting the data shows a real underdensity. The quest to settle this is driving some of the most ambitious galaxy surveys ever conceived. Projects like the Dark Energy Spectroscopic Instrument, or DESI, are creating three-dimensional maps of millions of galaxies, precisely measuring their distances and motions. These maps will either solidify the walls of the KBC void, proving we live in a cosmic bubble, or they will fill it in with unseen galaxies, restoring our faith in a uniform cosmos. Either outcome reshapes our understanding of our place in the universe. We are either privileged observers in a rare clearing, or our instruments have been quietly whispering a truth we have been reluctant to hear, that the universe's grand uniformity might have a startling exception, and we are living right in the middle of it. The possibility of a vast cosmic void around us forces a question about our galaxy's deepest past. What primordial events sculpted the Milky Way we see today? The answer may be written in the motion of billions of stars, and a recent discovery has revealed one of the most significant chapters. Our final strange object is not a single body, but a ghost. It is the Gaia sausage, the fossilized remains of a dwarf galaxy that collided with our own in a defining merger some 10 billion years ago. This ancient cataclysm was uncovered not by a new telescope peering into the dark, but by a satellite meticulously measuring the positions and velocities of over 1 billion stars. The European Space Agency's Gaia mission is creating an unprecedented three-dimensional map of our galaxy, and within that immense dataset, astronomers spotted a peculiar family of stars. These stars share a distinct chemical fingerprint, slightly different from the Milky Way's native population, but their most telling trait is how they move. Instead of orbiting the galactic center on circular paths within the disk, or even on the more random orbits of the halo, these stars follow highly elongated radial paths. They plunge in from great distances, swing close to the galactic center, and then rocket back out again. When scientists plotted these extreme orbits, they traced out a shape that resembled a sausage, hence the playful yet descriptive name. This orbital signature is the unmistakable hallmark of a galactic collision. The theory is both elegant and violent. A dwarf galaxy, perhaps 1/5 the mass of the early Milky Way, ventured too close. The immense tidal forces of our galaxy did not simply strip it apart, they shattered it. The stars of the dwarf galaxy were not gently absorbed, they were flung onto these wild, plunging trajectories, their original orderly orbits scrambled into a chaotic, radial spray. The energy of this impact was so tremendous that it did more than just add stars to the halo. It is believed to have violently puffed up the thin disk of the young Milky Way, scattering stars and gas to much greater heights and contributing directly to the formation of the galaxy's thick disk, that distinct component of older stars that surrounds the brighter, thinner disk we see today. In a very real sense, the Gaia sausage is a fossil of our galaxy's adolescence, a relic from the time when the Milky Way was still building its identity through violent mergers. This discovery recontextualizes our home. We are not living in a pristine, isolated spiral. We are living in a galactic monument built in part from the cannibalized remains of another galaxy. The stars from that long-dead dwarf are still among us, their strange orbits a permanent record of the impact that helped shape everything we see. They are the final proof that our galaxy's story is written not in peace, but in collisions, a saga of construction through destruction that continues to this very day. The galaxy we call home is a gallery of the impossible. From the silent, all-encompassing pull of the Great Attractor to the stellar vampirism of the Black Widow pulsar, from the ancient light of the Methuselah star to the shattered remains of the Gaia sausage, we have toured a cosmos that defies simple explanation. These are not anomalies, they are the rule. The Milky Way is not a serene island of stars, but a dynamic and often violent ecosystem, a place of constant collision, transformation, and mystery. Its quiet spiral arms hide stellar zombies and diamond planets, its core echoes with the ghosts of ancient geysers, and its very foundations are woven from invisible dark matter and the cannibalized bones of other galaxies. Each object we have explored is a different dialect in the language of the cosmos, a piece of a puzzle so vast we are only just learning to see its edges. So the next time you look up at the familiar band of the Milky Way, remember the strangeness teeming within it. See it not as a static backdrop, but as a living, breathing entity, a cosmic stage where the dramas of creation and destruction play out on scales both humbling and profound. We want to know which of these 25 strange objects captured your imagination the most. Was it the perfect geometry of the red rectangle, the phantom shout of the wow signal, or the silent, crystalline surfaces of the magnificent seven? Share your thoughts in the comments below. If you are ready for more journeys to the very edges of understanding, be sure to subscribe. Our exploration of the universe's deepest mysteries has only just begun.